In this example, we're going to take a look at modeling with trig functions to take a look at basically how much light is given off by the moon every night through a 1 month period. So the data in this question is actually real data from November 2019, and there's quite a bit of it here. I'll just scroll down so you can see it all. You're not going to have to, of course, memorize this or anything. We're going to use this information in Desmos, but I'll do that. You don't just trust me that I got these numbers correct. What I do want to point out is that it helps if you understand what a full moon and a new moon is. A full moon is the brightest it gets. That's where you see the entire circle in the sky, and it is 100% illuminated compared to its other illuminations. It's as illuminated as it gets. And then there's a new moon, which you don't see at all. It's complete darkness, and it occurs when you have 0% illumination. So what we'll do is we'll go over to Desmos and see what these points look like if I graph them. Okay, so I've typed those values in. Actually, that's a lie. I cheated. I cut and pasted a list from a document in. But either way, they are there, or at least it looks like they should be there, but there's nothing on the graph. And the reason for that is that our axes aren't correct. So we're going to have to modify these a little bit. And I'll remind you that this is over a month. So we're basically going from 1 to 30. So I'm going to change this to the X scale to -2 up to 32. And I'll try to step by 1. It doesn't like it because it would make it too crowded. So I'll try stepping by 2. Okay, that'll work. That should be fine. And I will point out that the Y values, the brightness values that we're looking at, are going to range between 0 and 100%. So I'm going to change my Y-axis. I could do 0 to 100, but then the max and mins are right on the edge. So I'm going to do -10 to 110. Again, just to leave myself, oh, that's looking much prettier. And I'm going to step by 10 so I can see 10% increments. But again, that's not a huge deal. Okay, so a few things I want to make note of here. One, this is real data, so it may be trigonometry related. It may be very close to a trig function, but it may not be exactly a trig function. And because of that, the odds of actually modeling this perfectly are pretty slim to get it so that every dot is on the line. And we're not going to worry about that. We're just going to do the best we can with the information we've got. So let's set up a cos function. Again, you can use a sine function if you really like to, but I'm going to use a cos function because I find them easier to manipulate. You know where the peak is. The maximum should occur at 0. It's easy to move that around. And I'm going to call this function b at t, or brightness at time. You can call it f at x. You can call it y equals. Doesn't really matter. I just like to be descriptive with my variables when I can be. It makes the question a little bit more obvious. So we're going to use a cos function, as I mentioned. I'll put the double bracket in there, and you'll see why in a second. And right now you can see that graph of cos t at the bottom there, it looks like a straight line. And again, that's because cosine has a period of 360, and this graph is only showing values up to about 30. So it's only showing the first little wee bit of cosine. What we can do then is we can start right off the bat by fixing our period, which is easier than you'd think. Our k value, or the number that goes in front of the t here, is just 360 divided by period. The 360 crunches the graph down to a unit of 1, a period of 1, and then the bottom number expands it back to whatever period we want. And I don't know exactly what that period is yet, but we can figure it out. In fact, I'm just going to go over to the graph and say, we have a maximum here at 12 and a minimum here at 26. Those are 14 units apart, and that's exactly half a period. It goes from a max to a min. So if 14 units is half a period, then 28 units should be what full period. Okay, so that looks a little bit better, except that it is way too short. The amplitude is way too small, and it's obviously way too low. The good news is I know that if the moon goes between 100% and 0%, its average must be 50%. And that's going to be my C value, my vertical translation. So I'm going to put plus 50. Okay, that takes us through the middle. That's helpful. And our amplitude is also going to be 50 because it's going to go 50 above and 50 below the midpoint. There we go. We're 3 variables down and only 1 to go. And the last one's pretty easy to find. We want to move this peak here from 0 over to 12. So I'm just going to move it right 12, which means I put in minus 12 beside the t in the bracket. Now, does that model the data perfectly? It does not. Can we do better than that? I don't believe we can. It's because the data is not perfectly sinusoidal. It is actually a repeating periodic pattern, but it's not a regular sine or cos curve. It is or could be something more complicated, so we might have to introduce another sine or cos term in addition to this, which is way beyond anything that we're capable of doing. That's a very, very high level of mathematics to do. But this is not bad. This gives a nice approximation. A couple things that I do want to point out. First of all, I could put this fraction though as terms, but I prefer, this is the one time I like to leave fractions as they are, because 360 over 28 tells me that the period of the graph is 28. It's easy to read off that value as opposed to trying to figure it out. And I also want to point out that we could have modeled this using a sine curve as well. Because remember, sine and cos are the exact same shape. It's just they're shifted over a little from each other. So I'm going to change this to a sine. And the only thing I really need to do to fix it is to recognize that the phase shift is going to be a little bit different. So here for cos, we moved it from 0 to 12. Here we have to move it from 7 to 12, so right 5. So I'm just going to put down t minus 5. And there you can see that we've got the exact same graph modeled either using cos or sine. So again, it's really your decision, but I just find cos usually is easier because we know that the peak starts at 0, and it's usually easier just to read off where the peak is and move it over that much. Okay, that's it for graphing something like this. Again, I'm going to point out that the dots are not all on the curve, and nothing we can do at this level is going to change that fact. The best we can do is show where the max and mins are, and that the rest of the data is a little bit approximate.